Lesson 5.3, Proving Polynomial Identities. So actually this lesson is nothing super new. Here, I'll show you guys an example. Down here, the very first example is prove that the difference of cubes is equal to, well, exactly what they said just a few pages back. Here, if I look a few pages back, they didn't list this as a fact, right? And yeah, I showed in class, and this is in the lab recording, how you can actually prove it. So we kind of did this already. Right? They also gave you all these identities last lesson. Again, this is all in 5.2. I just flipped back a few pages. Right? But how could you prove these? Well, what you could do is just distribute this out and show that the right side is equal to the left side, which is exactly what they did here. Right? They said, is this left side equal to its right side? They put an equal sign with a question mark over it. And then they would step to the distribution. And the last step, they should get the left side is equal to the right side. So here, I'll walk you guys through. This is example one on page 275. Very first question is the difference of cubes really equal to, so equal sign with a question mark, what they claimed it was just a few pages ago. So the difference of those base values multiplied by and then x squared, it should go, yeah, plus xy and then plus y squared. Right? Well, a few pages ago they had a and b. Now it's x and y, but you guys see it's the same idea. And in class, I think I threw some numbers in. So right, like you could make x equal to 7 and y equal to 2, right? And you could work it out and over. Right? And so you could totally do that too. But here, so I know that I can distribute this x into each of these three terms, and then I can distribute this y also to each of those same three terms. So I'll get okay, 1, 2, 3, 4, 5, 6. I should get six terms. Okay. Wait, on the left side, I only have two terms. Is this really going to be equal? Well, let's just play around with it, see what happens. So x cubed minus y cubed. Okay. Is this really equal to? All right, let's try that. So x times x squared, that is x cubed. Okay. And then xy, that's plus x squared y. And then xy squared. Okay. And then we want to y. So negative y x squared. Well, yeah, maybe it's not here. I think I'm running out of room on the paper. Minus y x squared. Okay. And then minus xy squared. And then minus y to the power of 3. All right, so that looks like that. All right. Okay, so now what? Oh, well, I see I'm adding some terms and subtracting some terms. So are there any in common? Yeah, here's an x squared y, and here's a yx squared, which are really the same thing, right? You could actually multiply, right? You guys know multiplication is commutative, so you can multiply in any order. So this and this are the same thing. Well, except one's plus and one's minus, so they cancel out. And, oh, hey, same story right here. Xy squared, one's plus, one's minus. Those cancel out too. So all I'm left with is this x cubed and this subtracting off y cubed, which matches the left side. It does. So x cubed minus y cubed, the difference of two cubes, is in fact equal to, yeah, I'm getting the same thing. Okay, so that's the same. Okay. So what I just showed is that that beginning statement is in fact true. Right. Here, I'll do the same thing that I did in class. I'm just going to make up some random values of x and y, and I'll show you guys. Right. So suppose, I'll write out the word suppose, uh, x equals, what does say minutes go? Like 7 or something crazy. I'll say y is equal to, how about 13? I mean, that seems pretty crazy, right? 7 and 13. I just made up those numbers just kind of randomly. Okay, so would this be true? Let's see. So x cubed minus y cubed equals, well, that would be 7 cubed minus 13 cubed, which is 7 power 3 minus 13 power 3. See, this is giving me negative 1,854. Right? Well, I bet if I just run the same numbers, so 7 and 13 through this expression, I should get the exact same answer, exact result. See if that's true. So, see, got x minus y, and then x squared plus xy plus y squared. So that would work out like eh, um, 7 minus 13, 7 squared plus 7 times 13 plus 13 being squared. Okay. Let's see if I get the exact same result. So 7 minus 13, 7 squared plus 7 by 13 plus 13 squared. Okay, did I multiply that correctly? Let's see, make sure that's shown up on the screen. Boom, 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 boom. I think that's right. Yeah, that's the exact same thing. Negative 1854. So these are the same. Check that. Okay, so yeah, I proved it formally with variables, right, everything above this horizontal line. Okay. And then just made up some random numbers to show you one particular numerical example of how that could work out. Right? And it did. It matches. It all works. All works. Yeah. Right. Well, I probably won't do the numerical example on every single one of these, but I wanted to give you guys at least one of those so you can see it work out. Actually, this is a real just short section. They just have two examples here. So they got polynomial identities as it relates to some geometry question. All right, we got this triangle here, and they labeled the sides of the triangle. Okay, let's read this block paragraph and see where are they going with this. Your classmate claims that you can always create three lengths that form a right triangle using the following method. Take two positive integers, x and y, where x is greater than y. The two lengths of a right triangle can be defined as the difference of squares, which they labeled down here, so they're giving you a picture. So that's nice. Okay. And then two times the variables multiplied, so two times the product, so 2xy, which they put here. Okay. The hypotenuse then, if you had that, no, it's a very particular case, but assume you had that. In that case, your classmate is claiming that the hypotenuse is always x squared plus y squared. Is your classmate correct? Explain your reasoning in the context of polynomial identities. Now, you do have to know one more thing for this, which is a Pythagorean theorem. But I think everybody's probably known that for many years. So let's see if we can prove this with Pythagorean theorem, or we're going to test it with Pythagorean theorem. And if it turns out to be true, then awesome. Right? So this is example two, right here. So, um, right. See, would that be true? Right. Um, Well, let's see. Did they how did they set this original equation? Because I'm thinking it was Pythagorean. But yeah, right. They have the base squared plus the height squared equal. Okay, yeah, they fed it straight into Pythagorean. That's what I want to do here. So I'll say like a squared plus b squared should be c squared, right? So that's Pythagorean theorem. I'll spell it out. Pythagorean theorem. Right. So if you take that to be true, okay. Then let's plug in the space could be x squared minus y squared. Okay. So we're going to square that leg. And then the height of the triangle is, let's say, 2xy. I say, and that's being squared here. Okay. So there's the two legs squared and then the sum of that. And it equals. Now, I'll put a question mark over the equal sign because we don't know if your classmate is actually correct or not. I mean, he's making this claim, we're testing his claim, hence I'm going to put the question on the equals. And then for C is x squared plus y squared. And since Pythagorean theorem says we have to square that, I'll further square that. Okay. So is this left side equal to this right side? Now, normally how I've seen this work out is that you normally leave one side alone and then work on the other side. But I guess if you're really stuck, you could kind of work on both sides. Let's see, what did your book recommend doing? Actually, your book did recommend, it looks like, working with the left side and the right side simultaneously, and then see. Like, if at some point you get both sides are the same, then you would have effectively proved the identity, right? So, let's see, I can FOIL this out. Here, let me throw in a middle step just in case you don't see it. This is x squared minus y squared, and then that squared, that's the same thing as itself times itself. Right? Now, you may see that in your mind, so awesome if you did, but if you didn't, it looks like that. All right, then this is this, and is this equal to, and I'll do the same thing on the side, again, if it helps to see it. X squared plus y squared, and then squared would be just times itself again. Okay. Okay, so that I can draw my FOIL lines, FOIL, first, outside, inside, last, and then thing over here, first, outside, inside, last. Now, oops, I forgot my square on this one. Wait, there we go. But this is just a single term being squared, so I can just very simply square every individual value inside, and that'll work perfectly fine. And so that's it. So I got x to the 4, and then outside, inside, this is minus x squared y squared minus another x squared y squared. So it's minus 2 x squared y squared. And then negative y squared is positive y to the 4th. Then over here I have plus, now 2 squared is 4, and then that's an x squared and a y squared. Okay, so that's that. Everything on the left side would look like that. Is that equal to? So question mark on the equal sign. And over here I can FOIL all this out. That's x to the 4. Then I get x squared y squared and another x squared y squared. So that's 2x squared y squared, and then a y to the 4. Okay, so is the left side equal to the right side? Um, oh, well, okay, I have a couple of x squared y terms, the x squared y squared terms, so I can combine these. So I have like -2 something here and 4 something here, like -2 apples plus 4 apples, that would give you +2 apples, right? So here, I'll combine those. So x to the 4 plus 2x squared y squared plus y to the 4. Right? Is that equal to x to the 4 plus 2x squared y squared plus, oh, oops, so this was y to the 4, I meant to say. Oops, I'm going to go amend that. Because it was y squared, that would give you y to the 4. And that's y to the 4 right here. And yeah, the left side matches the right side. Bing. So that is in fact an identity. Yeah. So your classmate came up with this crazy looking example. Like at a glance, I would really, could that possibly be correct? Right? But yeah, you can test it out exactly like you're looking at right now. And in fact, it works. Bing. So that's an identity. All right, so I highlighted a few of these. Here, I'll walk you guys through. So prove each polynomial identity. I did give you 8 examples. I picked 2 of them. So number 7, I got p to the power of 4 minus q to the power of 4. So is that equal to, no, supposedly it is because it says prove each identity. So I guess that implies that these should work. P minus q, p plus q, and then that's all times p squared plus q squared. Right. Now, this particular one, right, there's probably a couple ways you could do this. Um, you could like try to factor this on the left side, right? Or you could see, I could distribute this. I could FOIL this on the right side. Let me go first, outside, inside, last, and then I'll bring in this other piece later. Let me do that. Just kind of play around with that, see what happens. P to the 4 minus Q to the 4. Is that equal to? Let's see, that'd be P squared. Now the outside inside, that's plus PQ minus PQ. So that just cancels. And I have minus a Q squared. Right? And that's all times P squared plus Q squared. Right? And now I can go another step because I can bring this term, this in, and I can FOIL. First, outside, inside, last. Let's do that. So P to the 4 minus Q to the 4. Is that equal to, see, P squared, that's P to the 4. Then P squared, Q squared minus P squared, Q squared. That zeroes out. So those inside, outside cancel. Outside, inside cancel. And then minus Q squared, that's minus Q to the 4. Yeah, bing, that totally works. So that is proven. Left side matches right side. And P, Q could represent like any pair of numbers, or you can plug in like 3 and 1,005, right? It'll always work for whatever you plug in for P and Q. Like number 8. Ooh, we have power 5. Okay, so they switched to A and B, it looks like. We have A to the 5 minus B to the 5. Okay. Now, supposedly that's equal to, see, A minus B. So I'll put a little question over this equals because we're going to try to prove this. A to the 4 plus A cubed B plus A squared B squared plus A B to the 3 plus B to the 4. Okay. How could I do that? Well, maybe I'll try like a superFlow method. So I'll take this A and I'll distribute it into each of these 1, 2, 3, 4, 5 terms. Then here, I'll switch each color. And I'll take the B and I'll distribute the B into each of these 1, 2, 3, 4, 5 terms. Right? So that'll give me 10 different terms. Ooh. And we'll see what happens. So it should simplify to this difference. So A5 minus B to 5. But we're going to find out. So A times A to the 4. Well, there's my A to the 5. Okay, so that looks like a promising start. Right, then plus A to the 4B, then plus A to the 3B squared, then plus A squared B3, A squared B3, then plus AB to the 4. Okay. Right. Do you guys notice that the power on A decreases by 1, 5, 4, 3, 2, 1. There's an applied 1 here. And power on B is increasing. There are no B's here. There's one B here. 2, 3. Whoops, this was 4. Oops. Glad I caught that. Yeah. Okay. Now, I'm not finished yet. I just did all the peak distribution. I still need to bring in the b's. Now, I have a negative on the b, so I'm subtracting. So careful about that. So minus, and then, just to stick to the convention, I'll put all my a's first. So a to the 4b, a to 4b. You could do b, a to the 4. That's fine. It's the same thing. Then negative b, so that'd be minus a3b squared, then minus a squared b3, then minus ab to the 4th, and finally minus b to the power 5. Get 5. Okay, so let's like that. Ooh, okay, so hey, there's my negative b to 5, so that aligns. Okay, so this right here matches the left side, and this right here also matches the left side. I wonder if all these middle 8 terms cancel out. Let's see if they do. There's a to b to the 4, a b to the 4. Yeah, that those two subtract from each other. That cancels. Yeah, everything else cancels. So the left side totally matches the right side. Yeah, so that is good. We are on our roll. Yeah. Oh, these next two examples, we got some geometry looking examples, so that's fun. We got Pony claims that you can find the area of a square using the following method. Take two positive integers, x and y. The side length of the square, let's call it defined by the expression 3x plus y, which they very nicely drew out for you. We got 3x plus y and 3x plus y. Okay, so I can definitely visualize that. So that matches that. That's nice. The area can be defined by the expression. Okay, then they give you this funny looking expression. 9x squared plus 6xy plus y squared. Is a pony correct? Explain your reasoning in context of polynomial identities. Yeah, we can set that up as an expression. So if the side length of this giant square is 3x plus y, well, I know the area of a square is just the base times height, or that value squared, if you like. Right? So is that equal to, trying to prove, this expression that they gave you right here? They're claiming 9x squared plus 6xy plus y squared. Yeah. Uh, Keeping in mind, of course, x and y could represent any numbers. If you want x to be some number of feet and y to be a different number of feet or whatever, this could pertain to some real life scenario. Okay, so here, I'm going to slip in another step here. I'll write this expanded as 3x plus y times 3x plus y, just in case you want to see the foiling that's about happening behind the scenes. So is that equal to, of course, all this? It's just the same. Oops, I don't know why I did that. 6xy plus y. So there you go. That looks right. Okay, so is this equal to this? So let's do first, outside, inside, last. Foil the thing. So 3x, that gives you 9x squared. Then outside, inside, that's 3xy, 3xy, which would be 6xy. And then last, y is y squared. Okay. So is that equal to 9x squared plus 6xy plus y squared, which is straight out of the book? Let's see, that's that. This is squared. Okay. That's that. That's that. Yeah, it totally works. Bing! Math wins again. Oh, yeah. All right. Number 10. Ooh, another geometry situation. Got Julio claims that you can find the area of a rectangle using the following method. Take two positive integers, x and y, okay, where x is greater than y, so x is the bigger number. The side lengths of the rectangle are defined by the expressions 2x plus y and 2x minus y. And so just to compare that, what they just said, to this picture, you see how they shaded in that rectangle they're talking about in blue. So we're just focused on the blue part. So the width of this rectangle is 2x, and then plus this extra y right here. And the height of this rectangle, well, they start with 2x, but then they subtract off this y, so it's really just this height right here. So the width is 2x plus y, and the height is 2x minus y. Ah, you said. Right. And supposedly the area is defined by 4x squared minus y squared. Is Julio correct? Well, let's find out. So I know that the area of a rectangle is equal to width times height, or you could say length times width, or whatever. I'm calling this width and I'm calling this height. So area is a function of x and y would be, let's see, the width is 2x plus y, and the height is 2x minus y. Okay? Now, Julio is claiming, so do equals with a question mark, because we don't know if Julio is actually correct or not, that it's equal to Where was it? 4x squared minus y squared? 4x squared minus y squared. Okay, so is this correct? Well, uh, I can do first, outside, inside, last, because I know the area of a rectangle. I got that set up. I can just multiply that out, make a polynomial. That's fine. So 2x, 2x, that's 4x squared. Outside, 2x minus, so 2x times negative y. Inside is 2x times positive y. That's going to cancel. You see the outside, inside cancel? Here, I'll go ahead and write it out. Plus 2xy minus 2xy. Okay. And then finally, minus y squared. Okay, so is that equal to 4x squared minus y squared? Let's see if Julio is correct. Well, I said this is going to, that's right here. 4x minus y squared, 4x minus y squared. Yeah, Julio knows his math. That's what he's talking about. That is correct. Yeah. Okay, so these are all working out so far. I would say yes. Okay. Determine whether each equation is an identity. Okay, now the implication, the way they're wording that is these might be a little ambiguous. Maybe some of these work and maybe some of these don't. Actually, I did do a sneak peek into the teacher's edition ahead of time. So between 12 and 13, um, one of these should work and one of these should not. So let's find out which one's which. Number 12, I got x plus 2, x plus 1, quantities, or well, x plus 1 being squared. Okay, is that equal to? And then I got on the right side, x squared plus 3x plus 2, and that's all multiplied by x plus 1. Okay, so it's the left side equal to the right side. Okay. Here, I'm going to rewrite those x plus 2, x plus 1, and then another x plus 1 if you like. Okay, it helps to see that. Is that equal to x squared plus 3x plus 2, and then x plus 1. Right. Now, there's a couple ways I could finish this out. One way is I could do some FOIL, FOIL here, and then further distribute afterwards. So I could make a giant polynomial looking on the left side, and I could also distribute this on the right side, and I could do that. Right. But I think there's a faster way. And the faster way is I think I can factor this right here. This looks factorable, I think. Okay. So let's see. If I try to factor that, right, and I'll leave the x plus 1 exactly where it is. So that'll just stay locked in place. Can you think of two numbers that multiply to 2 and add to 3? I think the answer would be 1 and 2. 1 times 2 is 2. 1 plus 2 is 3. Which makes me think this should factor like this. X plus 2, x plus 1. And see, if you check your work, you can do FOIL. So first, x is x squared. Bing. Outside, x. Inside 2x. Add that to your, you get 3x. Bing. Last, 2 times 1 is 2. Bing. Yeah, this totally factors like this. Which exactly matches the left side. Yeah. So true. That is an identity. The left side is the right side. So the original statement from the book is correct. Right. Well, maybe I kind of spoiled the next one because I said I didn't want to pick one that did not work. So I think 13 does not work. But let's see if we can prove that. I got x plus 3 and then x minus 1 being squared. You know what? I might as well just save myself a step and write it out like this. Right. Again, just if it helps to see. Right, is that equal to, let's see, x squared minus 2x minus 3, x squared minus 2x minus 3, and then all times x minus 1. Minus 1. Okay. Well, if I'm trying to match puzzle pieces, I do see this in part does look the same. Okay. So maybe I could simplify the question, say, does that left there match that right there? Minus the part that I'm covering up. Okay. So how does this fit factor? Maybe I'll use the exact same method that I did with the last one. Okay. Because there's two main ways again I can take to finish this out. One way is I could do like a super distribution and make a giant polynomial on both sides and say did the polynomials match? Or I could try to go the other way and get it all in factored form. So is there a way to you know what? Okay, yeah. Can I factor this? Okay. I think I might be able to. Let's see. Are the two numbers that multiply to -3 and add to -2? I think -3 and +1. Is that right? X minus 3, x plus 1. Let me make sure I did that right. So xx is x squared. Bing. Outside, x minus inside 3x, that'd be -2x. Bing. And then -3 times 1, negative. Bing. Yeah, that totally factors like that. So is the left side equal to the right side? No, it doesn't work. So the x minus 1 is the place. That's okay. but this doesn't look like this, and this doesn't look like this. So say not an identity. That one failed. So 13 did not work. That one did not work. And um, yeah, I'll do one more with you guys. Right. This one worked out a little different. They gave you this table. I thought that was kind of interesting. Okay, but otherwise, it's relatively short and sweet here. Um, Consider the following equation. Here, I'll write it out so it looks better on the camera. We've got x minus 2 being squared, and then x cubed plus 9x squared plus 27x plus 27. Okay? And supposedly equal to, well, they just give equal to x squared minus 4x plus 4, and that's all multiplied by x plus 3 being cubed. Okay, let's put that in there. Okay. Evaluate the expression to complete the table. Oops. So let's break out a ruler, make a nice table. So we're going to plug in different values of x to this expression on the left, this expression on the right, and then there's some follow-up questions. But I think basically they're getting at the idea of, does the left side match the right side for these 5 individual points? Because if they match for 5 points, they're probably the exact same function, like hence this would be an identity, right? So we're going to say, suppose I call the left side f of x, and I call the right side g of x. I mean, that's pretty common, right? Okay, so f of x is this, g of x is this, just so I can simplify it in my table. So I'll come up with some x values. I'll say, what is f of x, which is this left expression? What is g of x, which is this right expression right here? Actually, they prescribed 5 x values. Okay, so let's go 0, 1, 2, 3, and 4, and just put them in. Okay. Now, I've been showing you guys a calculator trick that I'm going to use here. Whereas everywhere I see an x, I'm going to use the answer key. So second answer right here. Okay. And then I can very simply, within each of these values one by one, I can get the answers really fast. So I'll do answer minus 2. So I'm just setting up, like this first answer is going to be junk, but just to show you how this works. And that's squared, and then that's multiplied by x to the power 3. So I'll say answer to the power 3. Okay, make sure it shows up on the screen. Plus 9 answer squared. I'm just following this right here. I'm just copying. And we're saying x and putting answer. Plus 27x plus 27. Okay. So something greater than. But what if I plug in 0? Right, so now the calculator's thinking, okay, something about 0. I'm going to scroll up, and then as soon as I hit enter, then everywhere the answer shows up, it's going to plug in that 0. That tells me exactly what is that x. It says 108. Okay, 108. Okay, so what if I plug in 1? So 1, enter, then scroll up a couple of times, and then feed that into the expression. I should get 64. What if I plug in 2? Let's say, 0. Right? Do you see you could also graph, you could graph these, right? This could be coordinates. 0, 108 looks like a giant y-intercept. This looks like an x-intercept right here, we just did. Okay, plug in 3, get 216. Plug in 4, get 1372. Okay, now let's go into g of x, which at a glance looks totally different. I wonder if this is going to be the same thing. I actually don't know ahead of time, so I'm finding out as you guys are finding out, but we're going to see. I wonder if these. So open parenthesis, we got x squared. So let's do answer squared. There we go. Minus 4 answer plus 4. And then close open. So it'll automatically multiply. Answer plus 3. And that's all to the power of 3. Okay. So then what if I plug in 0? Okay, so now the factor's saying, okay, so I'm not 0. Scroll up a couple times, plug that in. It's 108. Huh. F(x) gave me 108. This new expression also gives me 108 when I plug in 0. That's interesting. What if I plug in 1? What if I'm going to get also 64? Let's find out. 1. Scroll up, plug in 64. Huh. Now there's 2 points where these two functions definitely match. Huh. What if I plug in 2? I get 0. 3 for 3. Plug in 3. 260. It's the same thing. It's matching. Does it match all the way down? Is it 5 for 5? We're going to find out. 1372. It is 5 for 5. It's the same all the way down. I wonder if I could plug in anything. I'll make up one more crazy value. Okay, let's plug in pi. Okay, so plug in pi. Something absolutely bonkers. I get 301.90 something something something. I'll just cut it off at the decimal point at one. Right now, if I take pi, so now I'm calculating thinking pi. Now I need to scroll way back to get something that looks like that other form. There it is. Okay, so I had to scroll way back to this original f of x. It gives me the same thing, 301.9. Okay. So now I just plug in a bunch of individual values of x, but I bet you could just solve this in terms of x. I bet if you use the same method we use for like most of this lesson, you could like expand all this out, like FOIL this and do a super distribution and similar thing on this side, do this cube and then distribute. But then the left side would look exactly like the right side, even in terms of x. Yeah, you see it with the table. They just wanted to give you guys a different perspective on this, different way to think about it. Right. So there you go. All right, there are your proving polynomial identities. Lesson 5-3.